Hello students, welcome to the course on Advanced Digital Communication and the course code is MCE 102. This is the course for Mtech EC first semester students. Myself, Dr. Surajit Boshak, Assistant Professor of EC Department, Guru Nanak Institute of Technology, Kolkata, and this is my official email address. Let us start lecture number 2 from the chapter of line codes. Actually, in the last class, we have covered various line codes. Why line coding is needed? What are the properties of line codes? And what are the different types of line codes techniques are present? Today, we discuss on calculation of power spectral density and bandwidth of unipolar format. And the lesson objective of the today's topic is compare the advantages of various line codes and analyze their system performance. And this topic is mapped with CO number 3. So let us start lecture number 2 from the module of line codes with the topic of power spectral density. So how power spectral density is being calculated of various line codes. Say this is a line coder. So we can represent all the discrete PAM signals in a single expression. This is the expression, say xt equal to summation over k equal to minus infinity to plus infinity a k p of t minus k tb, where ak is the coefficient, p of small t is the basic pulse shape, and tb is the symbol duration or bit duration, and which is the data signaling rate RB equal to 1 by TB. That means it's a bit per second. Now xt may be considered as a random process and each coefficient ak as a random variable. Now these coefficients may be generated by a discrete stationary random process which is characterized by the following relation between autocorrelation and ensemble average. That is Rn tau is equal to expectation of ak into ak minus n, where Rn tau is a autocorrelation function, E is the expectation operator. Therefore, the power spectral density of PAM signal xt is denoted as SF, which is 1 by TB mod of TFS square summation over n equal to minus infinity to plus infinity Rn tau e to the power minus j 2 pi NFTB, where PF is the Fourier transform of basic pulse shape PT. So in that way, you can calculate, or based on this formula, based on this expression, you can calculate the power spectral density of all the line codes. So let us first start the PSD of unipolar format or unipolar energet format. Now for simplicity, let us assume that zeros and ones are equally likely to happen or have equal probability. Therefore, probability of AK equal to 0 is same as probability of AK equal to 1, which is half. So, for n equal to 0, Rn tau equal to expectation of AK square, because Rn tau equal to expectation of AK. See in the last slide, AK into AK minus 1. So for n equal to 0, it is AK square. So amplitude square in an expectation, that means it is multiplied by its probability of occurrence. So AK may be 0 or it may be 1. So in case of 0, it is 0 square into half plus, in case of it is 1, then its amplitude is A, capital A. So A square into half. So it is A square by 2. Now we will calculate it for n not equal to 0. So there are the possible symbols are, so Rn tau equal to expectation of AK into AK minus n. So there are 4 possible values of AK into AK minus n, and these possible values are 0, 0, 0, 1, 1, 0, and 1, 1. And similarly, their product AK into AK minus n, that is the product of amplitude. In case of 0, it is 0 for unipolar. So product is 0, 0, 0, and last one is A into A, that is a square. And all sequences are equiprobable. So the probability of occurrence are 1 by 4, 1 by 4, 1 by 4, 1 by 4. Therefore, the autocorrelation function Rn tau for n not equal to 0 equal to 3 into 0 into their probability of occurrence, that is 1 by 4 plus a square into 1 by 4. So that would be a square by 4. Therefore, Rn tau for a square by 2 equal to, for n equal to 0, and for n not equal to 0, it is a square by 4. Now we move for the calculation of PSD SF, which is 1 by TB PFS square. So first term is for n equal to 0 term, so it is a square by 2, and rest of the term, that is a square by 4 e to the power minus j 2 pi nf TB, and the limit of the summation is n equal to minus infinity to plus infinity, but n not equal to 0. Now for simplification, if we add the term for n equal to 0 here, so obviously the outer term is a square by 4. Okay, come to the point. And what is PF? PF is the Fourier transform of basic pulse shape TB, which is nothing for a square wave, for a square signal. Fourier transform for a square wave is actually a sinc pulse. We already know it. So it is actually TB into sinc FTB, and it is PF square. So it is TB square into sinc square FTB, and outsider is 1 by TB, and we add in the series for n equal to 0 term, if we add there, then it should be a square by 4 plus n equal to minus infinity to plus infinity a square by 4 e to the power minus j pi 2 pi nf TB. So just break down it. A square TB by 4 first term, a square into TB 1 TB by 4 sinc square FTB. See, a square TB by 4 sinc square FTB. And the second term is a square by 4, a square TB by 4 sinc square FTB into summation term e to the power. So a square TB by 4 sinc square FTB into a summation over n equal to minus infinity to plus infinity e to the power minus j 2 pi nftb. This equal to 1 by TB summation over n equal to minus infinity to plus infinity delta function f minus n by TB. So it is a delta function. So that is why here it is written as 1 by TB summation over n equal to minus infinity to plus infinity delta of f minus ntb. So the PSD of unipolar energy format is denoted as SU energy F equal to a square TB by 4 sinc square FTB plus a square by 4 sinc square FTB into summation over n equal to minus infinity to plus infinity delta function f minus n by TB. Now, if we go for the calculation of PSD of unipolar RZ format, then what is the difference? The difference is like that the signal unipolar RZ, so at TB by 2 it will return to 0. So the only difference is here PF. So PFS square, that means at TB by 2, here instead of TB it now becomes TB by 2 for only for the calculation of PF. But remember that this e to the this TB is not becomes TB by 2 as it comes from the Fourier transform. So only difference is here, this TB by 2 and this sinc pulse TB by 2. So that becomes now TB by 2 whole square sinc square FTB by 2, and ultimately we get the result, that is a square TB by 16, because here 4 comes and already 4 already present. So a square TB by 16 sinc square FTB by 2 plus a square by 16, because TB cancel, this TB and this TB cancel. So sinc square FTB by 2, and remember that here it is not, it should not be TB by 2, because it becomes actually comes from the e to the power term, and which actually comes from the Fourier transform. So please note that here this should be TB, not it should not be TB by 2. Okay, so this term delta function f minus n by TB. Now, how to draw the spectrum of this unipolar say RZ on NRZ, whatever. So first we draw the spectrum of unipolar RZ. So a sync pulse is present definitely. And what is the cutoff of sync pulse? Say this is a omega plane and this is 0 is now this is 2 pi by TB, 4 pi by TB, 6 pi by TB, 8 pi by TB. So it is RB, 2RB, 3RB and 4RB. And similarly here minus RB, minus 2RB, minus 3RB, minus 4RB. So this is the problem is that which point the sync pulse cut the omega plane. So one thing is that just FTB by 2 think on 2 pi. So the first point is 4 pi by TB. So 4 pi by TB is the first point. Similarly in the negative axis it will be minus 4 pi by TB. And if first cutoff point is 4 pi by TB, then definitely the second cutoff point is 8 pi by TB, and similarly it is minus 8 pi by TB, like that. So this is all about the sync pulse. And the second term is a delta function, that is a impulse added with the sync pulse multiplied with the sync pulse. So the first is the delta function, which is for n equal to minus infinity to plus infinity. So for n equal to 0, it is just f equal to 0. So at the point of 0, there is a impulse is present. See the impulse. Now for n equal to 1, it is 1 by TB, f equal to 1 by TB. 1 by TB means RB. See here, RB, that point is 1 by TB or RB. So RB. And similarly for minus 1 also, minus RB. Now for n equal to 2, that is 2RB. But in case of 2RB, there is no amplitude. It is multiplied with the amplitude of the sync pulse. So sync pulse is again touched with the omega plane. So there is no amplitude. So in that point, we will not get any sync pulse. Now again the sync pulse comes to the 3 by TB. So that means 3RB for n equal to 3. So here again see the zoom view or larger view. So here and again impulse is present, similarly here, and minus 3RB also. So in that way we can draw the PSD of unipolar RZ. And see the bandwidth is just primary lobe, bandwidth between the primary lobe, center frequency between the primary lobe. So that primary lobe is 2RB and this is minus 2RB. So the bandwidth is 4RB. So in case of unipolar RZ, the bandwidth is 4RB. Now if you draw the waveform of unipolar NRZ, and then definitely the cutoff point of sync pulse is, if it is 2 pi, then 2 pi by TB is the first cutoff point. Say here 2 pi by TB and 6 pi by TB. In that way you can draw the waveform for unipolar NRZ. Okay. Now based on the properties, 5 properties, we just find out the advantage and disadvantages of unipolar format. So first is actually all are the disadvantages. So first is it is simple to show that on-off signaling or unipolar signaling, it is called actually on-off signaling, because 1 is like a on and 0 is like a off. So it is simple to show that On-off signaling requires twice as much power as polar signaling. If a pulse of amplitude +1 or -1 has energy E, then the pulse of amplitude 2 has energy 2 square into E, that is 4E, because amplitude is square. So it is 4E. Now because 1 by TB digits are transmitted per second, so polar signal power is E by TB. Now for the on-off case, each pulse energy is 4E. Though on average, such a pulse is transmitted over half of the time, while nothing is transmitted over the other half. Hence, the average signal power of on-off signaling is 1 by TB 4E into its probability of occurrence, that is half, plus 0 into its probability of occurrence, that is half. So it would be 2E by TB. So which is twice that required for a polar signal power. Okay. So it is the disadvantage. Now on-off signaling is not transparent because a long string of zeros causes the absence of a signal and can lead to errors in timing extraction. Then excessive transmission bandwidth. In unipolar RZ, the bandwidth is 4 RB, and in UNRZ, the bandwidth is 2 RB. Still it is large bandwidth. It has non-zero power spectrum at DC, and it has no error detection and correction ability. Okay, so this is all about the unipolar format, and based on the properties we see that all the properties are mainly disadvantages for unipolar NRZ and RZ format. So in the next we move for the calculation of polar format. So let us stop here. Thank you.